Hi everyone, my name is Luis Paulo Melchior and welcome to the first episode of Prussian Blue Chemistry. Prussian Blue Chemistry is an initiative created to build a bridge within the organic chemistry community around the world. The channel aims to make complex concepts more accessible while showcasing the progress of modern synthetic chemistry. In today's episode, it's my pleasure to introduce Zack Firestone, a PhD candidate in SmithLab at Florida State University. Here, Zack will present his work on the total synthesis of two halicyclamines, highlighting an Enantioselective microaddition, a macrocyclic azavidic ligation, and stereodivergent lactam reductions. Zack, it is my pleasure to have you here as the first episode. Please, take it away.
All right, thank you so much for having me. So my work at the SmithLab has been focused on the total synthesis of marine natural products, specifically those from families related to those in the manzamine family. So these molecules do have some interesting biological activity. Notably, manzamine A in particular has promise as an anti-tumor agent. However, because of the difficulty in isolation of these compounds, and especially in acquiring significant amounts of them, biological studies are still somewhat limited. They've also achieved significant attention from the synthetic organic chemistry community due to their complex structures. So we have a total of 4 syntheses of manzamine A, for example, 3 of caramophytin, 1 of tetradehydrohalicyclamine B, and 1 synthesis of haloclonocyclamine C. And my research in particular has been focused on the research of those structurally related to the halicyclamines and the haloclonocyclamine C. So going through a little bit of the history of these molecules, the first of these molecules was synthesized by Sulikowski in 2010, synthesizing haloclonocyclamine C and dihydrohaloclonocyclamine C. Their method utilized a Stille coupling to bring the two 6-membered rings together and utilized ring-closing metathesis to close the macrocycles. And they were able to achieve these in either 19 or 21 steps, depending on which molecule you're looking at, and this was a racemic strategy. The first of the halicyclamines was synthesized by Firstner's group in 2022, again utilizing, in this case, this time a photocatalytic cross-coupling to bring the two 6-membered rings together, and then using ring-closing alkyne metathesis to close the macrocycle, and then utilizing SN2 to close the second macrocycle. This one was achieved in 16 steps, and again, this is a racemic synthesis. So we chose tetradehydrohalicyclamine B as our target. This molecule has never been synthesized in any way by organic chemists. So looking at our retrosynthesis, begins quite similar to Firstner's synthesis, where we disconnect the second macrocycle, and then the second side chain can be installed via an alkylation of this lactam. Now, our strategy differs from the previous methods because we're actually going to build the piperidine ring from this imine and malonate. And then this macrocyclic imine can come from a novel macrocyclic azavidic reaction, and the malonate can come from the 1,4 addition into the enal. And then this intermediate was envisioned to come after a Wittig reaction and a Stille coupling. So there were a couple unknowns coming into the synthesis, the main one being the macrocyclization using the azavidic reaction. So it is known that you can use the azavidic reaction to build rings, but usually they're only used to make like up to 7-membered rings and maybe one 8-membered ring in the literature. So using it to make a macrocycle was unknown previously. We also weren't sure about how easy it was going to be to make this enantioselective, considering that none of these molecules had been made asymmetrically previously. And finally, we wanted to know, can we utilize different reduction conditions in order to access both diastereomers of the natural products? So looking at the forward synthesis, we start from our inexpensive dibromopyridine, and then we start with a Negishi coupling of this organozinc acetal to install the carbons, and then after hydrolysis with 1.5 molar HCl, we get this aldehyde in 76% yield. From there, we're able to bring on the rest of the carbons for the first side chain via a Wittig reaction, which again installs the rest of the carbons as well as gives us the alkene we need in the first side chain. Next, we install the enal needed for the organic catalysis via this acrolein surrogate, followed by acidic workup to cleave the acetal as well as the THP group. and now we need to switch the alcohol for an azide. So we did a 1-pot mesylation in DMF, and then we just added sodium azide to displace it, again, all in 1 pot. So the first kind of key step of the synthesis is up next with the 1,4 addition of the malanates, which we're able to do with Jorgensen's catalyst in DMF. And this reaction gave us 92% yield and 96% EE. And then the next step right after is the key macrocyclic azavitic reaction, which was a surprisingly simple reaction to run. We simply, just by heating the azide with triphenylphosphine and toluene at 40 degrees, we're able to get the macrocyclic imine. The problem with this intermediate is that it's not very stable, so instead of trying to isolate it, we just, again, added cyanoborohydride and acetic acid all in 1 pot, giving us 52% of the overall of the 2 transformations. Now from there, we need to make our lactam, which we were able to do by first doing a dealylation and decarboxylation with palladium tetrakis and dimethyl barbituric acid, which gives us the mono acid, which we can then do a amide coupling with HATU in order to give the lactam. Now this is kind of where we ran into our first significant problem with the synthesis, which was alkylation to install the carbons for the second side chain. And this was quite surprising that this gave so many issues when you look at the precedent set by Firstner in his synthesis, utilizing almost exactly the same intermediate, just with an alkyne in the side chain rather than an alkene. They were able to get 91% yield using exactly the same conditions, but we saw no reactivity at all. So after some discussions with Dr. Zakirian, he suggested using diethyl zinc as an additive. And that was kind of the magic that was needed to make this work, after some optimization, we were able to get 93% yield and a single diastereomer of the desired product. From there, we needed to reduce the lactam, which we were able to achieve with 10 equivalents of red toluene at 80, giving a modest yield of the piperidine. And from there, we just needed to close the final macrocycle, which we did via an in situ Finkelstein with sodium iodide, followed by SN2 to form the pyridinium. We were able to form this product in 44% yield. So the synthesis was 10 steps overall, highly enantioselective, and every step was strategic. We did encounter a problem, though, which was that the spectrum of this product did not match the spectrum of the natural product. So after doing some extensive 2D NMR analysis, we were able to determine that the molecule was very close, seemingly, but there were some discrepancies, specifically in this kind of bottom side chain here. When we look in, especially in position 8, some of the hydrogen or some of the proton shifts were off by as much as a full ppm compared to the natural product spectrum. So we're not entirely sure what the problem is. We're still there's the subject of some ongoing research, but it does seem to be that there's a problem with this bottom side chain. So looking at the synthesis of the cis natural product, epi-tetradehydrohalicyclamine, we start from the previous alkylated product using the same alkylation, except this time we're doing a different reduction condition, this time using Vasquez complex, TMDS and toluene. That gives us kind of an initial reduction, and then cyanoborohydride acetic acid gives us the epimer of the previous compound. So this is now the cis piperidine product, which we can then subject to the same final macrocyclization conditions, sodium iodide and acetonitrile, to give us the epi-tetradehydrohalicyclamine B in 39% yield. Again, similar to the previous synthesis, this was also achieved in 10 steps, highly enantioselective, and it was 100% strategic. So in conclusion, these are the first 2 enantioselective synthesis of any of these haliconocyclamine or halicyclamine derivatives. This is also the first synthesis forming the trans ring juncture about the piperidine. And we're hoping to expand this research to include, this route to include more natural products of these families. And I'd just like to quickly thank my group members, specifically my former mentor, Tiago, who started this project and passed it off to me after he graduated. And I'd also like to thank my good friend Felipe for helping me with bringing some starting material forward, as well as optimizing a few of these complicated reactions. And if you'd like to know more, you can read the paper in JAX with the link in the description or with the QR code on screen.
Now, Zack is going to talk about some specific transformation in depth, going through the mechanisms and reactions that he performed in his photosynthesis. Zack, take it away again.
All right, so we're going to start by talking about the stereodivergent reduction and why we get two different diastereomers depending on which reducing conditions are used. So the simple one, which is just using red al, which maintains the stereochemistry. This reaction starts by just simple hydride addition into the lactam, which then creates this aluminum intermediate with that hydride still on the aluminum, which can then reduce or do a further reduction and maintain the stereochemistry without touching the stereocenter. However, if we look at the Vasquez reduction, things get a little bit more complicated. So the Vasquez complex in TMDS does this initial reduction down to this NO-acetal, but it does not reduce further. Instead, we will first ionize the acetal with acetic acid, giving us this iminium, which then very quickly isomerizes to the enamine, which ablates the stereochemistry. Now, when the enamine is reprotonated with acetic acid, we get down to the cis epimer. And this occurs because the protonation of the enamine only occurs from the bottom face. So that means that we only get the cis product out. It never goes back to the trans. And then after its production with cyanoborohydride, we get the cis natural product, or the cis piperidine. So now we're going to look at the zinc enolate. This always generates questions whenever we give this talk in real life, and as to why the zinc, or what is the zinc doing and why does it help the reaction. So the reaction begins with simple deprotonation of the alpha position of the lactam with LDA, and then the DMPU additive chelates to the lithium and leaves behind the bare enolate. And when that occurs, you add diethyl zinc, which grabs onto the oxygen of the enolate. Now, diethyl zinc is a very electron-rich zinc species, which pushes more electrons into the enolate, raising the HOMO of the enolate and allowing this reaction to occur. And finally, we're going to look at the azavitic reaction. So this reaction is, despite being very useful, I don't think is as well known in the synthetic organic chemistry community. So it starts similar to a Schrödinger reduction, where a triphenylphosphine attacks the azide and creates this four-membered intermediate at the bottom left. This then undergoes a retro 2+2, releasing N2 and leaving behind a nitrogen ylide. This ylide can then go and attack an aldehyde similar to a regular Wittig reaction, again giving a four-membered intermediate, which then undergoes retro 2+2 again, releasing triphenylphosphine and giving us our imine, and then that imine can be further reduced with cyanoborohydride and acetic acid to give the macrocyclic amine.
I thank you for attending to this seminar, and I hope you enjoyed this talk. I appreciate you, Zack, for being so thorough about your chemistry, and stay tuned for the next episodes. See you there.